So today we're going to talk about the laws of thermodynamics and how they relate to reactions and other things. We're going to just reiterate some of the things that energy controls. As energy conversions occur, some of it converted into usable and some is unusable energy in the form of heat, more entropy, or heat energy can do work, but only if there's a heat gradient. So we can give off heat that isn't usable. We can make things less disordered, which isn't always usable. So if we think about a vehicle, there's an energy input, the chemical energy in the gasoline. As the gasoline bonds are broken, there's energy that is released. We have tables and charts of all the energy in the bonds of the gas. And the energy output is the mechanical energy used to turn the drive shaft of the car, plus we have unusable heat. Vehicles are 25% efficient, and 75% of the energy in most vehicles is unusable energy that goes out the exhaust. Free energy is the energy that is available to do work. Remember, the amount of free energy in a system is always lower than the total energy of the system. So 100% of the usable energy goes in. This is the loss of usable energy in a closed system, and it represents, the arrows all represent energy transfers. So the energy from the fuel is transferred into heat or into mechanical energy or in the friction of the wheels, the tires on the ground. The second law of thermodynamics tells us that over time in a closed system, there's a decrease in the amount of free energy available to do work. As a result, the entropy of the system will continue to increase because of that relationship that I showed you at the beginning between enthalpy and entropy. This continues until the system exhausts all of its supply of free energy. So what do we mean? We mean that the natural law of things are that entropy increases. Entropy is a measure of disorder. And so things naturally go from ordered to disorder. And so over time, you can see that this house has increased in entropy. It's very orderly here and it's very disorderly here. Everything goes from order to disorder. Free energy decreases, there's an increase in the disorder of the system. It takes free energy to maintain a system's order. Entropy is a measure of this disorder. That's your delta S that we've talked about. So there's more free energy here as we first put in the things, and as they all disperse or diffuse, we now have more disorder. This is how osmosis occurs across cell membranes and many other things. All living things need a source of free energy to live, grow, and reproduce. Most autotrophs rely on the sun for radiant energy. Heterotrophs rely on the food that they consume. During a chemical reaction, bonds are broken and bonds are remade. The chemical energy of the reactants will be different from the chemical energy of the products. This is how we have our delta H. Our delta H is found by subtracting the energy of the reactants from the energy of the products, and that tells us whether it's endothermic or exothermic. It tells us whether we're going to have to heat up the reaction or whether heat is going to be given off in the reaction. If you mix 2 moles of hydrogen gas with 1 mole of oxygen gas, nothing will happen. But if you add just the tiniest spark to the container, or even a static spark, this will happen very quickly, and you will have water form. The delta G for the reaction of hydrogen and oxygen is negative 58 kilocalories per mole. In order for it to be produced, the oxygen has to, so the intermediate or the transition state is where the oxygen has to break apart. So the oxygen molecule needs to break apart so that it can come and combine with the 2 hydrogen molecules because they're both diatomic. And this is how water is formed. This is why forming water is an exothermic and also both exothermic and a negative delta G. Ergonomic. All right. Energy of activation. Remember these charts from when we looked at the thermodynamics unit. The energy can be used to break the bonds in the reaction so they can form the products. This energy, this hill, as you recall, is the energy of activation. I didn't show you all the parts with the disorder component there, but it is part of this process. And so the difference between reactants and products overall, including the entropy and the enthalpy, is delta G. We were looking at solely the heat when we did the thermodynamics unit. So we were looking at just the delta H. But this other component needs to be added to truly understand why reactions are spontaneous or not spontaneous. So let's take a look at this reaction, and we're going to concentrate on enthalpy only for a bit and for the first homework assignment. So in this reaction, our reactants are CH2 gas and oxygen, and they're going to combine to make carbon dioxide and water. So my products are here and my reactants are here. The sum of all the products multiplied by, or added together, subtracted by the sum of all the reactants. We do also need to consider our coefficients of our balanced equation when doing this. You will be given a sheet. I will send it in the class files, and it will give you the molar enthalpy of formation so that you can find that. On the first sheet, I also have made a list of those molar enthalpies. These have been calculated experimentally, and they're available in many charts for us, so I will give you those numbers to help you out. Notice that these are per 1 mole. So again, this has 2 moles of water, so we're going to have to multiply the number here times 2. So let's go ahead and set it up where we have delta H of the products minus the reactants. So because there are 2 moles of water, I'm going to multiply it by the 2.85, 0.8 kilojoules per mole. I'm going to add it to the 1 mole of carbon dioxide in the product, and I'm going to multiply that by, because there's only 1 mole, by the 3.93 kilojoules per mole. I put parentheses here because we need to do these additions first before we do the subtraction. Next, we need to figure out the sum of all the reactants. Because these are just 1 mole, and because oxygen gas has 0, we don't need to consider it in the reactants. So we're going to go ahead and multiply 2 times 2.85 and then add negative 393. Be really careful with your negative signs because notice this is a minus, this is a minus, and that's going to give us a plus. So when you add these up, you're going to get 965 kilojoules per mole for the reactants minus negative 74.81, or plus a positive. And so I'll subtract that out, and I will find that the delta H for this reaction shown using these numbers that were given is negative 890.3 kilojoules per mole. So that would definitely be an exothermic reaction. Later, we'll put these pieces together and look at the entropy and see if this would be a spontaneous or a non-spontaneous reaction. Because remember that temperature times the delta T is another component. Your standard molar enthalpies will be given at a room temperature of 25 degrees Celsius. If it's any different, I will let you know. I will always give you the numbers to help. I'm going to go ahead and put some homework that is just figuring out your enthalpy or your delta H's. And I want you to practice those. And then tomorrow I'll continue on and we'll talk some more about entropy, and then we'll work on putting the pieces together and doing a few equations like that. Thank you again and have a wonderful day and keep up the great work.